Hello Math 1224, this is Dr. P with Lesson Launch 10.1, one volume, two methods. So in this video I am going to take the problem that you see here in blue, which is I've given you a region bounded by three things: the graph of y equals the square root of x, the graph of the line y equals 6 minus x, and the positive x-axis. So R is that region. We're going to revolve that around the y-axis to create a solid and ask what is the volume of that solid, and we're going to solve this in two different ways. So this is going to take a little bit, but I want to illustrate how the different methods of slicing work on the same problem. So the first thing you might want to do before we get started is you might want to pause the video and see if you can create for yourself a good sketch of the region and a good sketch of the solid. This is part of the process. Usually when I ask you to do one of these for homework or on an exam, I'm probably not going to give you the picture. I'm going to give you a description like this verbally and ask you to come up with the picture, and developing a good picture is part of the process of thinking through the geometry of this problem correctly. So you might want to just pause for a bit and see if you can create that picture. Anyway, the great thing about having you do that is you can pause it, but I'm just going to go on right ahead, because if you're still listening, it probably means that you're ready to move on. So let's see if I can create a picture of the situation I've described here. Just put that over here in the corner. There we go. So I'm going to create a set of coordinate axes. I think everything here is happening in the first quadrant for the most part, so I'm going to focus on the first quadrant, x, y axes. Alright, and I've got the graph of y equals the square root of x. That's going to look like this. That's not very good. Let me try that again. Should have a vertical tangent here and then continue to increase. That's a lot better. And then I'm going to put another graph. That's going to be the graph of y equals 6 minus x. Not going to try and be too precise about this right now. I'm just going to put a line there. In fact, that line should go on, but it's probably going to be the part in the first quadrant that matters the most here. So the region that we're looking at, let's pick another color, something a little bit lighter this time. The region that we're looking at is this. This is R. And we're going to revolve that around the y-axis. So to develop a crude picture of the solid that we're looking at, it looks like the region is going to be shaped kind of like this. It's going to have some point here, and then it's going to come down like this. And then as I rotate, I'm going to pick a different color. There we go. So I'm going to get something with a circular base, and then it's going to have a circular top, although there's going to be sort of a hole down in the middle of it. Okay, my drawings are pretty crude. I've seen that some of you in this class have far better drawing skills than I do. So anyway, I just try to draw this well enough so I can start to get an idea of what's going on. Okay, so that's a pretty crude picture of the solid that we're looking at, but it's a start anyway. Okay, so I'm going to talk about how to solve this problem by slicing this figure in two different ways. First way I'm going to try slicing the figure is slicing horizontally. So I'm going to take a typical slice here. It's supposed to be a rectangle there. And then think about revolving that around, try that one more time, revolve that around the y-axis. So I'm going to get a small disc with a hole in the middle of it. This is actually coming up pretty good. This is probably the best drawing I've done so far on this tablet. So anyway, that's a typical disc. Actually, not a disc, but a washer, as we talked about in class. That was part of the presentation we saw yesterday, was that this figure, it is a solid. It's a solid with a very small depth, dy, and it's a circular washer with an outer radius and a very small, in this case, inner radius. And I'm going to call the outer radius big R and the inner radius little r. You might find that to be a useful convention for yourself as well. Now, those radii, they're not going to be the same throughout the entire figure. That outer radius starts out pretty big and gets smaller as we go up. The inner radius starts out at 0 as at the bottom of the figure and gets bigger as we go up. So both the outer and inner radius are going to be functions of how high we are. That's r of y and little r of y. And part of our task is going to be to figure out what those radii are as functions of y. So anyway, let me just zoom out here and remind us what we're dealing with. Because I think if we're going to find the right functions of y here, we're going to have to base those on the information that we were given up here. This is going to play some part in figuring out what those are. All right. So let's see. So the inner radius, that seems to be determined by this curve here. The inner radius seems to be determined by the curve y equals square root of x. And that's going to be the value of x corresponding to whatever y is here. That's that value of x is going to tell me how big my inner radius is. So if I have y equals the square root of x, then that's equivalent to the relationship x is equal to y squared. And that kind of makes sense as you look at this. When y is 0, x is also 0. But as y increases, x starts to increase very quickly. It increases quadratically if you sort of tilt your head so you can see x varying as a function of y. So that r of y, that's going to be y squared. Okay, what about big R of y? Well, big R of y seems to be determined by this curve here, or by this curve in this picture. So big R of y appears to be determined by the equation y equals 6 minus x. And if I try to put that value of x, that is, this value of x here, in terms of y, I'm going to get x equals 6 minus y. So I believe that big R of y is going to equal 6r of y. Sorry, r of y is going to be 6 minus y. My bad. Anyway, so I think those give me the outer radius and inner radius. Now, before I start setting up an integral, the thing I need to do is figure out what the volume is. What is the volume of this thing? What is the volume of this thing? So to do that, I think what I need to do is first think geometrically about what the volume is going to look like. Well, that volume is going to look like the area of that annulus. Annulus is just a fancy name for the area between two circles. It's going to be the area of the annulus times the depth of the washer. And that's going to be pi big R squared minus pi little r squared times dy. Remember, these were both, let me zoom out a bit more. I realize things are starting to get kind of small here. There we go. Now remember, big R and little r both were functions of y. So I want to actually represent that here. I'm going to pull that factor of pi out and then rewrite big R and little r as functions of y. And I think that's going to be pi, and then big R of y was 6 minus y, that's squared, minus, and then little r of y was y squared, and then that's also being squared, dy. And then I could simplify that to pi times, I think that's 36 minus 12y plus y squared minus y to the fourth dy. All right, so now I have something that might be that I could use as an integrand, so that I can add the volumes of these washers together. Now, as I'm adding the volumes of the washers together, I need to think about where those washers start in this figure. That is, what's the minimum value of y, and then what's the maximum value of y for which I have washers, because those washers don't go on forever. There's a place where they stop, and I need to figure out what that is. Well, the place where they stop is going to be determined by this intersection point here in this picture. What is that intersection point? Well, we can find the intersection point by thinking about these two equations here, the ones that we started with, because that's going to be the point where these two equations have a common point, or that is a common solution in x and y. So let me just come over here. This is a little subsidiary piece of work here. So where do y equals square root of x and y equals 6 minus x, where do those intersect? Well, one way I can figure that out is I can treat this as a system of equations, where this is one of the equations and this is the other one, and use substitution. Since I have y equal to 6 minus x and square root of x at the same time, I could write 6 minus x equals the square root of x. And then one standard way of solving that would be to square both sides. That actually doesn't feel like that much fun. I'm going to wind up with I'm going to end up with an x over here, but then a quadratic over here. Not sure I want to do that, actually. I think that any way I solve this is going to turn into some kind of quadratic. But I think, for simplicity's sake, I might take this and rewrite this as x equals y squared, and then substitute that into this equation here. So I'm going to get y equals 6 minus y squared, since x was equal to y squared. And then that gives me y squared plus y minus 6 equals 0. That'll factor into y plus 3, y minus 2 equals 0. And then since the product of those is 0, I need to have y plus 3 equals 0 or y minus 2 equals 0. So y has to be negative 3 or y has to equal 2. So y could be 3, y could be negative 3, or y could be 2. But if I look over here, you'll notice I don't have much interest in y being negative 3 here. Y is going to be some positive value. And that positive value is going to be, the other one that I got, it was y equals 2. So this here is the line y equals 2. So I think now, and I know that this solid is going to begin at y equals 0, so I think I'm going to have slices all the way from y equals 0 to y equals 2. So I think we're ready to integrate. Total volume is going to be the integral from 0 to 2 of pi times this gnarliness, 36 minus 12y plus y squared minus y to the fourth dy. Let's just go ahead and pull that factor of pi out. And I think, I think I'm ready to go ahead and start taking antiderivatives. This is 36y minus 6y squared plus 1/3 y cubed minus 1/5 y to the fifth. That's from 0 to 2. And now I just have a bunch of calculation to do. This is a terrific example setup on my part here. I probably should have picked something a little bit easier to pick on, but I think I can work this out. First of all, one nice thing about this is this entire mess, it's 0 when y is 0. So I really just need to worry about the value when y equals 2. Thank goodness for small favors here. So I get 36 times 2 is 72, minus 6 times 2 squared, I think, is going to give me 24. 1/3 times 2 cubed is 8/3. And then 2 to the fifth is 32, so I'm going to have 32/5 there. Ugh, gross. Okay, so that's pi 48 plus 8/3 minus 32/5. And at this point, I kind of feel like getting out a calculator, but I don't have one handy. So I believe if I calculate all that out, let's see. I'm just going to put it all in 15ths. This is, if you're still watching, God bless you. I'll be done here in just a minute. This is going to be 40 15ths minus 96 15ths, I believe. So I believe I'm going to get, let's see, 760 minus 96 would be, I think that's 664 15ths pi. Okay, so I'm going to stop this video here because I'm already at about 14 minutes. And I will take up the question of how to solve this using a different slicing method in the next video. And if by some miracle we still get 664 15ths pi, we will throw a big party here. Anyway, that's it for this video. Stay tuned for the next.